Hello, everyone. My name is Amin Ahmad. I'm founder and CTO at Vectara. And with me today is a friend from my Google days, Ka Wong. So, Ka, thank you so much for joining us. And if you don't mind, just briefly introduce yourself and tell us a little bit about your background.
Sure. Well, thanks for having me on here. Um, my name is Ka. My background is in statistics, so I got a PhD in statistics from UCLA. And then I went to Google and I spent sweet 12, 13 years at Google. And I worked with different teams initially with the search team, doing a lot of model evaluation. Then I gravitated towards research, brain, and machine learning type stuff. And I've always had a strong interest in data, model evaluation, and just thinking about what are the interesting data problems that can further power different machine learning models.
Okay, okay. Well, thank you for that background. And the reason we're talking today, as you know, Vectara provides a serverless platform for retrieval augmented generation. So companies that want to take advantage of that pattern involving generative AI without the hassle of running their own infrastructure and things like that, they can use Vectara. And one of the things that we've recently introduced is something called a factual consistency score. So every time Vectara is doing something like generating a summary based on a set of retrieved facts, this score will basically indicate uh, our system's confidence that the summary is factually consistent, which means it is consistent with the underlying facts that were retrieved. So one way of looking at it is it's an attempt to quantify hallucination in the system. And one of the features of this score is that we've paid attention to try and actually perform something called calibration or probabilistic calibration. And that's where I think, Kai, your ability to explain things and your background in statistics could come in helpful for our viewers here. If you could, maybe you can just begin by explaining, what is calibration in the first place?
Well, calibration to me means you take a model that may perform really well in terms of accuracy, and then you push it even further, and you ask that the model outputs predictions that actually correlate well with um, probabilities that we observe in practice. So, for example, you can have a very good ranking model. Like when you go to Google and you issue a query, you get a list of search results. Now, the ranking algorithm behind that is very, very powerful. But that's a different problem. That's a ranking problem because Google has to always return you a set of results. It doesn't get to choose. It cannot, it cannot return any result. But in a lot of real world machine learning applications, we're not just, we want the model to be accurate in terms of ranking result and producing outputs, but we also want the model to produce these outputs that we can interpret as probability. So for example, like if you have an algorithm that is doing medical diagnostics, um, it's making a decision one way or another. It's either true or false in terms of classification. But how confident we are about, the classification label is very important because if we are very, very confident, then we'll make, a set of decisions differently than if the model is, guessing on a on a coin toss. And so I think calibration, means that we require the prediction scores to have a strong probabilistic interpretation.
So one of the issues then is, if you look at modern neural networks, they're oftentimes outputting values in the range of 0 to 1. And the natural tendency is to actually just interpret those directly as probabilities. But what you're saying is those might be valid scores for ranking purposes, but not actually be calibrated. Am I understanding correctly?
That is correct because you're so when you put a softmax layer on top, you can always map the score to the 0, 1 interval. Now, if you're calculating, let's say, true positive or any ROC or AUC type number, they're only looking at the relative rank ordering of the items. But when you actually go in and take a look at the distribution of the score, what you'll find sometimes in practice is you'll see that the score distribution is bimodal. So a lot of the items are pushed against 0, and a lot of items are pushed against 1. Okay? Now, we don't know if that correlates to the actual distribution we observe in practice, but a lot of models tend to behave that way. And I think one of the reasons why a lot of models behave that way is because they've been overly optimized. They're overfitting the data. And so, when you overfit, you'll get overly confident, on the right-hand side and on the left-hand side. Everything looks like a, hard positive, everything looks like a, hard negative. When you do the rank ordering, the model may still be able to rank these items very well. But then, when you correlate, the probabilities, the distribution to, actual observed probabilities, you may be very surprised because what you'll see is there are a lot of items that the model is very confident about. And when you look at the data, the evaluation data, out of distribution data, not out of distribution, but like held out data, you'll see that the model is actually not confident at all. So you'll make a lot of mistakes, even within, this class of, predictions that is labeled at, let's say 0.99% confident. And so we can take those numbers on their face value.
So what you're saying is, if I'm understanding correctly, that essentially for a developer, an average developer out there, the value in knowing that they're working with a calibrated score is in knowing that they can directly interpret those numbers as what? As probabilities or likelihoods of correctness? Is that what it is?
Correct. So if you have a well-calibrated model and it's outputting a score in the 0 interval, 1 interval, if you take an example, and it's labeled as 70%, 0.7, what you want is if you take a lot of those examples that are all labeled at 0.7, you want to be correct. You want the predictions to be correct on average 70% of the time. But in practice, you have to go out of your way to make that happen. Just because you've finished training your model, just because it's outputting scores in the 0-1 interval, doesn't mean that 0.7 means 70% of the model being correct.
Okay. Well, thank you for that explanation. I guess as a professional statistician, I'm curious what your thoughts are now with the rise of machine learning and artificial intelligence everywhere, on why maybe some kind of background or understanding of statistics may be more important than it has been in the past in software development. If you had any thoughts on that.
Sure. Well, I think one of the biggest concerns I have about these very powerful models is that they've grown so large and they've grown so complicated, and they've always been black boxes, that it is hard to understand. It's hard to characterize their behavior. For example, when I went to grad school, in statistics, we built models. We love building models to try to describe the world. And there's, statistical models, they always are very transparent. You actually build a mathematical equation, these are regression models. And so you know exactly what, variables are going into your model, how they interact. You control the whole structure of the model. You describe, you write it down in pen, paper. In machine learning days right now, we don't do that anymore. We leave everything up to the neural network to figure out. Now, what that means is we have given up a lot of control to the machines. All that we can do is specify a loss function that makes the most sense to us and make sure that we don't overfit. And then for the rest of it, we just feed it lots and lots of data. And then we hope that our evaluation metrics, go up, iteration after iteration. There's not a whole lot of uh, there's not a whole lot of ways for us to go in and inspect the model and make sure that it's doing everything as expected. Everything is performance driven. And so that's one of my biggest, worries is that, um, you know, in a lot of ways, we've ceded control to the machinery, and we're only controlling a few high-level knobs. As a result, for example, if you can have a very powerful model and it can be highly accurate, but at the same time, if you look at the output score, it may not be interpretable at all. But once again, these models have not been built to be interpretable. They've been built to predict. So they can make good predictions. That's one thing. But on the other hand, as I said earlier, we should push the model. We should push the models harder so that we have a better understanding of what they're really doing, so that we can make more informed and educated decisions.
Yeah, and I think that's going to be particularly relevant now as software systems are directly trying to do decision making on the outputs of these models, and understanding what the output means is more critical than ever.
Yes, we used to, build these regression models, and we would interpret each coefficient independently. We would run a p-test to get the statistical significance, and so there's a very good understanding of, the whole, the behavior of the model. And right now, everything is just, driven by the performance metrics.
Absolutely. Well, Ka, thank you so much. I think this has been very helpful for me and hopefully for the audience as well. I think just to wrap it up, you've recently started a new venture, System 2 AI. Maybe you could say a word about that and what you're trying to tackle.
Sure. The company is called System 2 AI. It's System 2 is a popular reference to a very popular psychological model of the human mind. System 1, System 2, System 1 is when we're in a stream of consciousness, when we're acting on autopilot. And System 2 is when we slow down and make intentional, deliberate decisions. So we think that LLMs right now are very capable System 1 models. And if we want to really build very powerful AI systems, these systems, they need to be more deliberate, intentional. And one way to do that, the quickest way to achieve that, we think, is to integrate that, language models with symbolic reasoning, because symbolic reasoning gives you a strong handle on, precision, and decision making, planning. And so, if we can take, symbolic reasoning and language model together, we hope that we can, build agents, hopefully that can go out and help you achieve a set of goals, but with a plan, with a strategy. It's not just going with the flow.
Hmm. Right. Okay. Okay. Well, that sounds very interesting, and best of luck with that. And thank you again for joining us.
Thanks for having me.